Welcome back to another video on speech processing. In this video, we will look at forced alignment, automated forced alignment. Let's talk about perplexity real quick. It's a measure of how many choices you have at any decision point. And the fewer choices you have, the better your chances are of making the right choice. Right? So lower perplexity leads to better choices, and minimizing perplexity is the same as maximizing probability. The insight here is that the best language models are ones that best predict an unseen test set. And the best or better ASR performance is when you reduce the number of choices, right? Lower the perplexity. So for example, let's say we train an Ngram model of 38 million words from the Wall Street Journal. And if we're only looking at unigrams, we have a higher perplexity score here at the bottom of my screen. But if we look at bigrams, like take into account the previous word, or we're looking at the current word, trying to figure out the current word, then we have a lower perplexity, a score of 170 there. If we look at trigrams, the previous two words, when we're trying to figure out the current word, we have an even lower perplexity, so we have a better chance of getting the right choice there. Okay, so that's just an idea here with speech processing and other tasks. We're trying to decide what the current thing is given previous things. Let's review real quick what ASR is, automated speech recognition, right? It's a concept you're familiar with now. Here's just a quick diagram. We have a speech input, speech signal on the left-hand side, goes through the model, the system, and we come out with recognized words, right? Now, forced alignment is kind of like that, but we already have the transcript. We feed in both the speech signal, that is the sound, as well as the transcript, and we use the model to produce timestamps of words and phones. Okay, and let's just go back one slide. If you think about it, ASR is actually doing that. ASR is actually force aligning. It's going down to the phoneme level and say, hey, here's a phoneme I see right here in this time slice of this sound. It's doing that under the hood, but it doesn't actually give it out to us, doesn't report it to us. So forced alignment is saying, hey, I want to see, well, it's a little bit different. I want to see those timestamps. I'll give you the transcript and the audio, and I want you to give me the timestamps of phones and words. Here's a model of cognition, human cognition. Number one, the subject or the person hears utterances, and the subject or the person forms representations from long-term memory and from short-term working memory, right? And number three, there's representation kept in the short-term memory. And then number four, the subject forms sentences or utterances in speech, right? Utterances based on accessed representation. And, well, let's talk about the applications for forced alignment. Number one, training data for acoustic models. Acoustic models take a lot of training data to make a good acoustic model that's worth using. And you need audio as well as time-aligned phonemes, so that the training model, the system that's trained on it, can say, okay, within this little slice, I'm hearing a B. And so when I do all the analysis, the Mel-Kepstrom, frequency coefficients and whatever it does, it says, okay, this is all related to B, right? But that's extremely time-consuming and difficult and to do by hand for humans, right? And so it's not really a viable option to do that, to do the amount of hours of audio that needs to be done on to train up an acoustic model. So what if we already have words that are transcribed, for example, via ASR system, and we feed the audio and the transcript into an ASR system, and then we force the system to align the words with the audio signal, as well as force align the phonemes. And the output is a labeled timestamp for each phoneme. I mean, that's what ASR is. And so we can use this forced alignment system in order to create training data for an acoustic model. It'd be best to have a human go in there and kind of spot check here and there to see how it did before throwing it into a training system. So here's an example of time-aligned words and phonemes here on the right-hand side. Right-hand side of my screen, I have time-aligned words. So the beginning timestamp and the end timestamp of these words. Actually, just the beginning timestamp and the duration there. And on the left-hand side, we have actual phones with their timestamps. I believe milliseconds there. Okay, so that's what we're doing. That's what we want a system to do for us, is to time align. Forced alignment is great for annotating data for training, like I mentioned. And so being able to create a transcript with an ASR tool and then doing forced alignment with another tool is what we need to create some training data. And this can be used to do all sorts of linguistic work. Application 2 of forced alignment systems is you can look at specific acoustic properties of speech. Here's a message on Linguist List that was sent about a year ago from time of recording. It says, "Dear all, an MA student of mine is working for their final year project on a comparison of emotional speech in 3 languages." Those languages, good. And so they're looking for emotional speech. And like I mentioned, I've shown this a couple times in other videos, that we had a PhD student here recently at BYU create a large corpus of audio recordings of emotional speech. And 120 subjects, people. And so that is... Dr. Lonsdale responded to that message, said, "Hey, here we have all this audio data available. You can download all of it right there, all sorts of audio." So you can run forced alignment and find the vowels and extract features about the vowels, and then build a classifier to compute emotion from data. And the result is you have an emotion detector, machine learning model that you can use on speech, English speech. Perhaps even other languages. So this is great for targeting analysis of acoustic properties to do certain portions of speech. And so having those timestamps on words as well as phones within words is awesome, is useful. Another application of forced alignment is to do oral proficiency testing. So it's difficult to do a good oral proficiency testing because it's human intensive. You need a human there, and that makes it expensive to do. And because of that, most L2 programs that teach a second language do not systematically assess speaking outcomes on an ongoing basis. It's too cost prohibitive. So it's difficult to tell if you're making progress or not in teaching oral language skills. And so some standard methods of assessing oral proficiency is the oral proficiency interview proposed by the American Council on the Teaching of Foreign Languages, or ACFL for short. You have a simulated or computerized oral proficiency interview where a person just listens to a prompt and speaks into a computer, records response into a computer, and then later a human will have to go back and listen and grade those or rate those. Let me back up to the first one. The oral proficiency interview is a live interview with someone over the phone or in person. There's interaction, live interaction. Whereas the second one is asynchronous. Person responds to prompts that a computer is given, that is given on a computer, and a human later listens to it. These down here, this elicitation imitation tests are interesting. And it's a kind of a proxy for proficiency, I guess. Even the OPIs and the simulated OPIs and the computerized OPIs are as well, just kind of proxies for proficiency. The idea with the last one here, elicited imitation tests, is that an L2 speaker of a language hears an L1 speaker say a sentence or an utterance, and the L2 speaker simply is supposed to repeat back what they hear. It's web-based, and it's cheaper to do. And, well, yeah, it can be cheaper to do. And they're scored later by humans. And the rationale is that there's this delicate balance between making an item too short and when they're just simply working on working memory. It turns into a working memory task, which is what we're trying to do. We're just trying to get more than just working memory. But if the elicited imitation item is too long, then it's impossible to repeat even for native speakers. And if it's too complex, even native speakers won't be able to repeat it. And if it's too simple, then it won't be able to discriminate between the L2 levels or the non-native speaker levels there. And if it's just right, then it has necessary knowledge of vocabulary and syntax and semantics and consolidation to bring those together and to be able to repeat back. So creating elicited imitation items is a linguistic engineering task itself, trying to find good items. And you can also use forced alignment to score these responses. So here are some examples. Let me play a couple here. I'll play all of these. So here's sample one. Here's a native speaker speaking.
An actor sang the song to us.
And here's a level 1 speaker trying to repeat that back.
An actress saying she want to work. She want to work.
Yeah, didn't quite get it. We could hear she's trying to make the sounds she heard, but yeah. Here's a level 5 speaker trying to say that same sentence.
An actress saying she want to work.
Oh, sorry. That was a level 1 again. Let me get this down here.
An actor sang a song to us.
Okay, so just listening to those repeated sentences allows humans to say, okay, this sounds like this person's at level 1 versus level 5. Here's another sentence. Here's the native speaker.
Hesitating before she spoke her next line, the actress reached the pinnacle of her nervousness.
Okay, here's level 3 speaker trying to say that sentence.
Too hard, I could remember it. Please help me. Please, please.
He's not in dire danger. He's just saying, I could not get that at all. Here's a level 5 speaker trying to say that same sentence.
Hesitating at the first time, the actress hesitated her first line. I don't know what.
Right, it's a complex sentence. Here it is again.
Hesitating before she spoke her next line, the actress reached the pinnacle of her nervousness.
It can be somewhat difficult for even native speakers, right? Just thinking through, okay, you have to remember there's like this adverbial clause thing, hesitating before she spoke her next line. Anyway, here's another sentence.
He had a voracious appetite, the height of a towering weed, and the strength of a malicious, rancorous hippopotamus.
Right, you have to be pretty advanced in English to remember, number one, remember all that, understand it. Like there's this, listening, comprehension part, remembering, and then producing. And anyway, so elicited imitation tasks are kind of a proxy for gauging proficiency, and they're cheaper and quicker than a longer oral proficiency interview, which can last up to like 20 or 30 minutes. And these are scored, so the EI, or elicited imitation responses are scored by syllables. So here's a French sentence that the person got every last syllable correct, and so got a score of 1. In this number 2 sentence, the speaker missed a couple syllables in here, so ended up with a score of 0.75. And this very long one that was hard to remember and get everything, they forgot a whole big chunk of these sentences or syllables here. It ended up with a 0.42 score. And so trying to get some good sentences, like I said, is a meaningful, important task in itself, because some sentences discriminate well. Like on the left-hand side of this slide, let me show the whole slide. You can see that these sentences do a good job. Perhaps he works there. They have to understand what perhaps is, and had you ever flown that high before? Right, we have this pluperfect, had you ever flown? And a couple more, the second from bottom's bullet there. When she went to Las Vegas, did she like the shows that she saw? We have this temporal adverbial clause before the actual question there. On the right-hand side, we have some sentences here that don't discriminate very well. Have you slept? Maybe he likes cats. We eat cookies. How do good children play baseball? Anyway, so the idea here is that just trying to come up with good sentences to use in an elicited imitation task that can later be fed into a forced alignment system to see how well the person did is an important task in itself. So an elicited imitation task was created here at BYU. I wasn't involved with that creation, but it was created in order to deploy on the web, and it was they used the Sphinx 4 ASR model, which does force alignment as well. And you count how many syllables match the transcript is the idea there. And they did several languages here, and It was used here in BYU language classes as well as at the MTC. Excuse me. And they got really good correlation between human rating of unelicited imitation tasks, as well as the ASR or forced aligned computer generated score. Good correlations between the humans and the computer system rating these elicited imitation tasks. Here are some plots showing the correlations. So on the left-hand side of the screen, we have on the x-axis we have a human score, and on the right we have the ASR system, the forced alignment score. You can see that sometimes it was more generous. The ASR system was more generous here. It was giving a score of 0.4, like right in here, when the human was only given 0.2. But overall, it's pretty well correlated there. Here's another plot there showing the correlation between the human on the x-axis and the ASR system on the y. With Japanese, you can see that if the ASR system were identical to the humans, then all the points would right on that diagonal line. They're not. It looks like the ASR system was a little bit more generous on the lower proficiency areas than up at the higher ones. So it's a great tool for evaluating and critiquing language learner speech. And it's open source technology. There's a lot of systems out there that can be trained up and used to do forced alignment and to be applied to looking at L2 proficiency. And it correlates well with human scores. So here are a few tools. My voice is pretty weak this morning. Sorry. Tools and systems for forced alignment. CALDI is it's written in C++, and it is a good system. I think I mentioned previously that we had a student, undergrad student in linguistics here at BYU, who recently, a couple of years ago now, went to the master's program at the University of Edinburgh to do their speech processing master's program and applied for a job in Paris. And part of the job application process was to create some speech system with CALDI, with that software there. Sphinx, like I mentioned, we saw in a previous video, is a toolkit that does ASR but also does forced alignment, so you can use it to do alignment as well. Excuse me. The Vox API as well. Junius also does alignment. Montreal Forced Aligner is based on CALDI. It uses CALDI under the hood, and it is a good system. I've used this one successfully with Spanish and English. Those are the two main languages I research. It has a lot of pre-trained models, dictionary models, like the result of G2P, but also has G2P models itself. Like they've trained up a G2P model that you can then use to convert your graphemes, your words and orthography to some phonemic or phonetic representation. Acoustic models are sitting here. Language models like Ngram language models, and they have Corpora as well. Let's just take a quick look here. If we browse dictionaries, you can see they have all sorts of stuff, different languages, Arabic and Basque in northern Spain and Bulgarian. They have 109 entries in this list. There's Czech, English in different countries. Anyway, so a lot of resources there. That's the one I've used the most. I've used another one I don't have listed here for Spanish. It's only for Spanish. It was created by a PhD student at UC Berkeley in computational linguistics. That worked pretty good for Spanish, but MFA or Montreal Forced Aligner can do Spanish as well. Berkeley Fawn Lab Forced Aligner here. They have one. UC Berkeley has a good computational linguistics program. They have one. UC Santa Barbara also has one here. UPenn P2P, I gotta update that link apparently, but University of Pennsylvania has one called P2FA. McGill's Prozzi Lab Aligner is basically the precursor, if I understand it, the precursor to MFA, Montreal Forced Aligner. kind of been superseded by Montreal Forced Aligner. There are some Pratt plugins that can do forced alignment. If you can make these work, awesome. This one here is a Pratt plugin. Pratt Align, interactive Pratt plugin for performing phonetic forced alignment. Hasn't been updated recently, but may still work. Not sure. I think I tried it once and I can't remember if I got it to work or not. I just used MFA, honestly, to be right. Here's another plugin for Pratt if you'd like to look at that one. Darla is a web-based forced alignment that does vowel extraction as well under the hood. Or not under the hood, it actually uses MFA, Montreal Forced Aligner, under the hood to do forced alignment, and then it does vowel extraction analysis. It's a web-based one created at Dartmouth University. So that is another one that you can use for forced alignment. So, and here's a pointer of this person who just has a list of some of the forced aligners that he or she is aware of. And I've mentioned several of these already. Caldy there, Montreal Forced Aligner MFA, there's the P2FA. So let me do a little demo here of using MFA for you. So let's see if I want to let me get myself organized here. Let me grab this over here. So I got Pratt open right here. And let me show you the original. So here is the original recording. Let me just play it for you so you can hear what I'm saying.
I was creating a corpus in California of Mexican speakers and had 2 student assistants who were native speakers of Mexican Spanish.
Anyway, I'll just stop right there. So anyway, I have, what is this, 34-second recording of me talking about an experience where I missed, I lost a recording. I didn't realize the recorder was not recording on this really awesome interview with the mother, one of my research assistants, native speaker Spanish. Anyway, so I have the transcript that I produced with Whisper ASR. I gave this recording that I just played a little bit snippet of, gave the whole recording to Whisper and let it do its ASR. And then I grabbed, just copy and pasted the ASR into Pratt here into one interval. You can see there's just one interval that whole transcript is in, all the way down to the end. Let me just play the end.
And she had already left. I didn't want to ask her to, it was so annoying. It was
oops, I cut off a little bit at the end. Oh, there it is. Anyway, so I have the whole thing in here. In fact, I need to push this out over to here now that I'm looking at that closer. So the point is that MFA requires you to have your audio and wave and have a transcript either in a text grid, a Pratt text grid in one interval, or if you have little chunks, you can put them into separate intervals in Pratt, into intervals, text grid intervals in Pratt. Or you can use what they call a lab file, .lab file, which is based on the Prosody lab, forced aligner, the precursor to their MFA. Anyway, I'm going to go ahead and use this one here. Let me just save that real quick. I'm going to save it into my input directory. I'll explain this in a second. Let me just make sure it's called the exact same thing as the sound file right there. It should ask me to overwrite. I'll say, yeah, go ahead and overwrite that. Okay, so I just want to show you that's what I have set up. I have the audio and I have one big interval with the whole transcript. Again, it'd be better if you are able to slice it up into smaller intervals. It would do a better job. But let me show you if I bring my viewer over to this screen. So the way you have to have it organized is you have an input file with the waveform, or the wave file that is, and the .text grid file, the one I just showed you, that you can see back here behind it, that back there. That's the input directory. And then the way you use it, let me bring it up. I went through the setup to get MFA set up. And you actually use a Conda environment. Let me deactivate it to start from the very beginning. So right now let me just clear out. I'm in a terminal window, right, on my computer. And it is based on a Conda environment. So I'm gonna activate the Conda environment that I called aligner that allows me to use the aligner. So now I went from base to aligner. And you do MFA align, and then you give the pathway to the input directory that has the wave and the text grids. So let me do that. It's called input, right? So let me just jump back over to this. So it's in my downloads, it's in input, and there are the two things. So I just give the directory there. The next argument, let me refresh my memory on that. Let me bring up the documentation real quick, just so we can look at it together. If I just do, let's go to user guide and go to all commands and go to align. The next, so I give the corpus directory, the next argument is the dictionary path. So they have, like we saw, they have a bunch of pre-trained models, including dictionary files. And so I'm going to use one of theirs, and I already have downloaded to my hard drive. So I'm going to get it here. English.dict is the name of the file that has that. Next argument is the acoustic model path. So I will give that. I'm just giving the full pathway just for fun, just for pedagogical purposes, even though I don't have to give the full pathway, but I'll do so for pedagogical purposes here. And it's a .zip file, as you can see there, .zip. And then the last one is the output directory, and that is in my downloads as well. I call it output. In fact, let me go ahead and erase the output, what's in the output right now. I did it before I started the video. Let me just erase that. Now, if I let it go, it'll take a couple seconds here to work. Oh yeah, let me clean it up. Let's see. It's still working there. It's aligning, good. Telling what it's doing, and it's all done now. All right, they're all done. So now if I come back over to here, I should have, there it is, I have this recording, or excuse me, that text grid. So I come over to Pratt, let me come back over to Pratt, and let me dump that one and do it in, bring it in for you again. So if I'm in the input directory, but I want to go to the output directory. Go to the output directory here. There it is. Let me bring this in. Now if I select the sound and the new text grid that was just created and look at it, I have two tiers. I have words and phones. If we just zoom into one of these spots, let's just zoom into there. So here I was creating a corpus in California. Anyway, so it's aligned down to the words, and then within each word, let's just zoom in, you can see it's aligned down to the phones. So it's aligned down to the phones for me. So anyway, you can go from audio and pass it through an ASR system, take that and put it into a forced alignment system and get aligned words as well as phones in a very short time, relatively short time. Okay, let's go back to this point here. And all right, so that was a little demo of the Montreal forced aligner system. So yeah, for the next lab, you're going to work with some of these systems and use some files, a dozen files, at least 10 seconds in length, and do a forced alignment and evaluate the results, see how they do, and try some other models, other languages, maybe other people's speech. You can get some other people's speech, classmates or friends, try it with other people's speech as well. Okay, so that is forced alignment, another application of speech processing with tools. So let me know if you need help. See you next time.